This is Calculus Part 9. At the end of Part 8, we had a 3/4 inch shaft. Turning a 2-foot diameter pulley, which has a radius of 1 foot, with a rope and a weight hanging from it. The weight equals 123 pounds. So we're pulling 123 pounds up at the rate of 12,566 feet per minute. So the work we're doing each minute is 12,566 feet per minute times 123 pounds. 12,566 times 123 equals about 1.5 million. Actually, it was this number, 1,551,000 foot-pounds per minute. I rounded our actual weight down to 123. So anyway, if we're pulling 123 foot-pounds per minute, that many feet per minute, we're putting out this much power, 1.5 million foot-pounds per minute. Well, 33,000 foot-pounds per minute is a horsepower, so this divided by 33,000 gives us 47 horsepower. So now that we know the torque, our 123 pounds times 1 foot gives us 123 foot-pounds of torque on this shaft. Now that we know that, we can calculate the stress in our shaft. Remember this formula? Torque equals stress times the polar moment of inertia divided by the radius, and the polar moment of inertia is equal to pi times the radius to the 4th power over 2. So we could say it's stress times pi times radius to the 4th power over 2, and let's not forget that r. So we could just say, instead of r to the 4th over r, we'd call it r cubed. So we can say torque is equal to stress times pi times r cubed over 2. Okay, so of course this is equal to our torque way over here on the left. So if torque's equal to that, what is stress equal to? Well, let's multiply both sides of this equation by 2. So when we do that, we eliminate that 2 and we multiply that by 2. Let's divide each side of the equation by pi. So we get rid of that pi and slip a pi underneath there. Let's divide each side of the equation by radius cubed. So we eliminate that and write radius cubed here. And what we have is stress is equal to 2 times torque divided by pi times radius cubed. Well, our torque is 123 foot-pounds. So let's just go ahead and write 123 foot-pounds. For torque, well, 2 is 2, pi is 3.14159, blah blah blah. Okay, our radius, we've got a 3/4 inch shaft, and that's the diameter, so our radius is going to be half of that, and half 3/4 is 3/8. So let's just write 0.375. Can you see that? There we go. Inches. Okay, so let's figure our stress. 123 foot-pounds. 123 foot-pounds. Ooh, let's see, there are 12 inches in a foot, so let's turn that into inch-pounds. Times 12 equals 1,476 inch-pounds. Okay, times 2 equals 2,952 inch-pounds divided by pi, divided by invert pi equals, okay, now divided by 0.375 cubed. So divided by 0.375 equals, divided by 0.375 equals, divided by 0.375 equals, one more time. And that gives us 17,819 pounds per square inch. Stress equals 17,819 pounds per square inch. See where we got our units. We turned our foot pounds into inch pounds, and we're dividing by inches cubed. So inch pounds divided by inches cubed is pounds per square inch. So this is on the high end of the stress that's generally allowable on a steel shaft. It's okay for turning a hydraulic pump on a backhoe out on the farm, but if you were turning a propeller with the propeller shaft having that much stress, and then yanking the airplane all around and subjecting the propeller shaft to the bending moments that come from gyroscopic precession, you might be flirting with trouble there, so might not want to have quite that much stress on a propeller shaft. Let's say we didn't have the formula that we just used to calculate the stress that results from our torquing this 3/4 inch shaft. Let's say that we were going to estimate the stress in it by dividing our 3/4 inch shaft into a bunch of concentric rings. Okay, here's 3/4 of an inch diameter, so it's 3/8 of an inch radius. So let's say we have a circle here that's 1/8 inch radius. Here's a little ring. It has an ID of 1/8 of an inch, or an inner radius of 1/8 of an inch, an outer radius of 2/8 or 1/4 of an inch. And here's our outer ring. It's 2/8 or 1/4 from there to there, and it's 3/8 from there to there. Okay, so we're gonna draw arrows here to the middle of each ring. So if this is 1/8 of an inch from there to there, another 1/8 from there to there, another 1/8 from there to there, well then the length of this arrow is between 1/8 and 2/8, so it'd be 1.5/8, which is 3/16. So hence the radius to the middle of our middle ring is 3/16 of an inch, and the radius to our inner ring, which really isn't a ring but just a little solid shaft because its inner radius is 0, so it would be halfway between 0 and 1/8, which is 1/16. And the length of this arrow would be halfway between 2/8 or 1/4 and 3/8, which is 2.5/8, which is 5/16. So let's figure the area of each ring here. Well, the area of a circle is pi times the radius squared, or you could say pi times the diameter squared over 4. Doesn't matter which formula we use. So the radius of our inner circle is 1/8 of an inch. So I can say 1 divided by 8 equals that many inches. Okay, now squared. Okay, times pi equals 0.049087385. Okay, that's where we got that number from. And our middle ring, well, the area of the middle ring and that circle inside it would be pi times that radius squared. Well, that radius is 2/8 of an inch, or 1/4. So let's say 0.25. That's our radius. So square that, and we have 0.625. That's radius squared times pi. That's the area inside of this ring, but we just want the area of this part, so we have to subtract that area. So minus 0.049, all that, minus 0.049,087,385 equals 0.147262155. That's where we got that number, and we get this number by doing the same thing, figuring the area of the whole 3/4 inch shaft minus this number, which is, well, it would be minus that one and that one. In other words, just to get the area of that outside one. Let's see if we did that right. That'd be 3/8. 3 divided by 8 is the radius. Okay, squared times pi. Okay, that's the area of the whole thing. Okay, so that minus this 0.147262155 equals that. Now also minus that 0.049,087,385 equals, looks like I better go back and do my homework. Let me stop this video and I'll catch back up when I get it right. Yeah, this is the right number. Let's do it again. 3/8 radius, 3 divided by 8 equals, radius squared is that, times pi is that. That's the area of our whole shaft. Okay, minus this 0.147262155 equals that. Now minus the area of our inner circle, 0.049087385 equals, there we go, 0.245436926. That's where we got that number. Okay, so the stress of each circle, let's just assume that it's a stress halfway between the inner part of the circle and the outer edge. So with this first one, this is 1/8 of an inch from there to there, so it's 1/16 of an inch from there to the middle of it. So 1/16 of an inch divided by the radius of the whole thing, 3/8. 1/16 divided by 3/8 times the maximum stress, which is going to be out at the outer edge. So the stress here in the middle isn't going to be much. It's only going to be that divided by that. So 1/16 divided by 3/8 times the stress max is the stress in our inner ring. The stress in our middle ring is the length of this arrow, 3/16. Now there's 2/16, 1/8. There's 2/8, which is 4/16. Halfway between 2/16 and 4/6. Let's see, yeah, would be 3/16. Okay, divided by the radius, 3/8 times stress max. That's our stress at the middle of this ring. And here we have the numbers for the stress for the middle of the outer ring. And our torque contribution of each part will be the stress times our area, that number, times the radius. Okay, the radius to the middle of each ring that we're looking at. Let's go ahead and do one here. Okay, the stress is 1/16 divided by 3/8, which is 1/16 divided by 6/8, which is 1 divided by 6, so 1 divided by 6 equals, okay, our area is 0.049 times 0.049,087,385 equals that. Okay, times our radius, which is 1/16. Let's say just divided by 16 equals 0.005,11326. That's how I got that number. Well, you get those numbers the same way. When you add up all these torque contributions, we'll have our total torque equals that number plus that number plus that number, which is that number, 0.078233019 times stress max. The units for these numbers, this is in inches cubed, because inches cubed